Imagine stopping, not passing through, stopping and holding still 4 billion miles from here, somewhere in the middle of the Kuiper belt. You're inside the band of rubble that every diagram draws past Neptune, the wall of tumbling rocks at the edge of the map. Now look out of the window. Behind you there is one brilliant point of light, no larger than a star, which is the sun. In every other direction there is black, and the same constellations you can see from your own garden, in exactly the same places. There is no horizon, nothing moves. If you sat at that window for a year, nothing you could see with your own eyes would change. Your instruments would insist you had arrived. Your eyes would report that you were nowhere at all. By the end of tonight you will know exactly what you would really find out there, and it is not in front of that window. Get comfortable. If you're the kind of person who enjoys discovering that a familiar picture was never a measurement, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this, the word debris is going to sound like an accusation. Now, let's slowly settle into the dark. Somewhere in your memory there is a picture of the outer solar system, and it is almost certainly the same picture as everyone else's. The sun sits in the middle. The planets run outward in a line, getting colder and stranger as they go. And then, past Neptune, there is a band. A ring of rubble. Thousands of grey lumps drawn shoulder to shoulder, tumbling in a thick, crowded circle around everything else, like a wall of debris at the edge of a city. That band has a name, and the name is the Kuiper belt, and tonight we are going to go there. But before we leave, it is worth being honest about where that picture came from. It did not come from a photograph. There is no photograph. Nobody has ever taken an image that shows the Kuiper belt as a belt, because no camera has ever been in a position to see it as one, and even if a camera were, there would be nothing in the frame. The picture in your memory came from an illustrator, working on a page that had to fit on a page. The objects had to be large enough to see. They had to be close enough together to read as a group. Every diagram of every belt in this solar system has been drawn under those two constraints, and the result is a picture that is almost perfectly wrong in the one respect that matters most for a journey. So let us start with numbers instead of drawings, because the numbers are the only honest way in. 1 astronomical unit is the average distance between the Earth and the Sun. It is 149,597,870 kilometres, more or less, and light crosses it in 8 minutes and 19 seconds. That is the unit we are going to use for the rest of tonight, because kilometres stop meaning anything very quickly out here. Neptune orbits at about 30 astronomical units, so the inner boundary of the Kuiper belt, if we call Neptune's orbit the boundary, is a little over 4 light hours from the Sun. The conventional outer boundary, at around 50 astronomical units, is closer to 7 light hours. Now think about what a shell between those two distances actually contains, not the objects in it, the space. If you take a sphere with a radius of 50 astronomical units and subtract from it a sphere with a radius of 30, you are left with a volume of empty room that runs to hundreds of thousands of cubic astronomical units. And a cubic astronomical unit is not a small box. It is a cube 150 million kilometres on every side. You could set the Earth's entire orbit inside one of those cubes and still have room to spare. Into that volume, put everything we think is there. The best current estimates suggest something on the order of 100,000 bodies larger than 100 kilometres across, along with an unknown but very large number of smaller ones. 100,000 sounds like a great deal. Spread through that volume, it is closer to one object the size of a small country somewhere inside each of those 150 million kilometre boxes. That is the density of the wall of rubble you are shown. That is the hazard field. I want to be careful here, because this is the first place tonight where the correction is going to feel like a letdown, and it is not one. When people find out that the asteroid belt is not a crowded obstacle course, the usual reaction is a small deflation, as though something has been taken away. Nothing has been taken away. What has happened is that a cartoon has been replaced by something considerably harder to hold in your head, and much stranger to be inside of. A place that is dangerous to cross is a place you understand. A place that is impossible to perceive is not. Because that is the actual character of the Kuiper belt, and it is going to shape everything else we say tonight. It is not a wall. It is not a barrier. It is not a frontier in the sense of a line you cross with a sense of crossing it. It is a population. It is a statistical statement about where certain objects tend to be. made about a volume of space so large that the objects it describes are, from any point inside it, effectively invisible to each other and to you. Which raises the question this whole video is built around, and I want to put it plainly now so that it sits with you for the next 2 hours. If you actually went, if you built the ship and paid the fuel bill and crossed the 4 billion miles and arrived, what would you really find? Not what is out there in the catalogue sense. We can list the catalogue. What would you find in the sense of what would be in front of you? What would the light look like? What would you be standing on if you could stand on anything? And what would it mean that you had come? That is the question, and I am going to tell you honestly that the answer is not the one I expected when I started reading for this, and it is not the one the diagrams prepared me for. By the end of tonight you will have it. But it does not come from any single object out there, and it does not come from the distance, and it very definitely does not come from the danger, because there isn't any. So here is the shape of the trip. We're going to go out in stages, and each stage is going to make the previous one look naive. First, the leaving. What it actually costs to throw something to 30 astronomical units, why the entire journey is decided in the first 9 hours of it, and why nothing we have ever sent has been able to slow down when it got there. Then the crossing itself, and the long silence in the middle of it, which turns out to be an engineering discipline rather than an inconvenience. Then arrival, and the moment where the map says you're inside the belt and your eyes say nothing at all has changed. Then the light, which is the first thing tonight that is going to genuinely surprise you, because the Kuiper belt is not dark. Then the emptiness, properly, with the numbers, until the fear you brought with you inverts into a different fear entirely. And then we start finding things. A 35-kilometre object with 2 lobes that came to rest against one another at walking pace 4.5 billion years ago and have not moved since. A whole population of objects out there that exist in pairs, and the reason those pairs are the single best piece of evidence we have for what happened at the beginning of the solar system. A world with a ring where a ring should not be able to survive. A world spinning fast enough to have been pulled out of shape. 2 more that appear, on the evidence of light collected by a telescope 1.5 million kilometres from Earth, to be doing chemistry in their own interiors, at temperatures where you would expect nothing to be doing anything at all. And then, near the end, the 2 facts that reframe everything else. The first is that 99% of the Kuiper belt is missing, and we know roughly where it went. The second is that the outer edge of it, the neat boundary at 50 astronomical units that appears on every diagram, is being quietly dismantled right now by a dust detector built by university students, which has been reading numbers for the last few years that a belt ending at 50 astronomical units should not be able to produce. That is the trip. It is a long way out, and we are in no hurry. One more thing before we go, and then I will stop preparing you and we will actually leave. Everything you're going to hear tonight about what these places look like up close comes from a total of 2 encounters. 2. One at Pluto in 2015, one at a small object called Arakoth on the 1st of January 2019. Both were flybys at 14 kilometres a second, and between them they add up to less than a day of genuinely useful close observation, spread across 13 years by a single spacecraft the size of a grand piano that is still out there, still working, and running slowly out of power. That is the entire close-range human experience of the Kuiper belt. Everything else we know from watching stars blink out, and the machine that gave us those 2 days is currently looking for something to look at and has not found it. The intuitive picture of a journey to the outer solar system is a rocket with its engine lit, pushing steadily outward for years, the way a car drives across a country. Almost nobody holds a different picture, because almost nobody has been told a different one. And it is wrong in a way that changes everything about what the trip is. A chemical rocket burns for minutes, not years. Minutes. Everything after that is falling. The spacecraft we're going to follow tonight is called New Horizons, and it left Earth on the 19th of January 2006 on an Atlas V rocket in its heaviest configuration, 5 solid boosters strapped around the core, and a 3rd stage bolted on top of the payload. The payload itself weighed 478 kilograms. That is roughly the mass of a grand piano. It was made small on purpose, and understanding why it was made small is the key to understanding the entire journey. The reason is the rocket equation, and the rocket equation is one of those pieces of physics that sounds like an accountant's footnote and turns out to be a wall. It says this: if you want to go faster, you need propellant. But the propellant has mass, so you have to accelerate the propellant too. So you need more propellant to accelerate that propellant, and more again for that. The relationship is not additive, it is exponential. Every increment of speed you want costs you a multiplication of the mass you have to lift, which means there are only two ways to go fast. You can build an unimaginably enormous rocket, or you can make the thing on top of it very, very light. New Horizons went the second way. A grand piano on top of a stack designed to lift something several times heavier, and the result was the fastest departure from Earth ever recorded. 16.26 kilometres per second straight off the pad. It is worth being precise about what that record is, because there is a faster spacecraft and it does not help. The Parker Solar Probe has been clocked at something like 192 kilometres per second, which makes New Horizons look sedate. But Parker's speed is borrowed. It is the speed of something falling toward the sun, and it is handed straight back on the way out again, the way a dropped ball hands back its speed when it bounces. Speed you fall into is not speed you can leave with. The only number that matters for a journey outward is how fast you were going when you stopped being able to push, and on that number, nothing has ever beaten the piano. It is a January afternoon in Florida. The count runs down and the solids light, and the sound arrives at the viewing site a few seconds later as a physical pressure against the chest rather than a noise. The stack climbs. The 5 boosters burn out and fall away in pairs, and the vehicle keeps accelerating, and then the core stage goes, and the second stage burns, and then the third stage, the one that was added specifically because this payload had somewhere very far to be, spins up and fires, and for a few minutes something the mass of a piano is being pushed harder than anything humans have ever pushed away from this planet, and then it stops. Everything stops. 45 minutes or so of engine time total, across the whole stack, and after that there is nothing left to burn and nothing more to do. The spacecraft is coasting, and it will be coasting for the rest of its existence. 9 hours later it crosses the orbit of the Moon. Apollo took 3 days to cover that distance. New Horizons did it before the end of the working day, and it did not slow down for it, and there was no one on board to notice. By the time the first evening was over, every decision that mattered about the next 13 years had already been made. The speed was set. The direction was set. The arrival dates at Jupiter, at Pluto, at everything after that were all already written into the shape of the trajectory. A spacecraft on a coasting path is not travelling in the sense a ship travels. It is falling along a curve that was fixed in the first few minutes, and the only thing that remains is to wait for the curve to arrive somewhere. That is the first thing that makes this journey different from the one in your head. It is not an effort. It is a throw. Even so, 16 kilometres a second was not enough. At that speed, from Earth, Pluto is about 13 years away, and 13 years is a long time to hold a project together. So the trajectory did something else, and this is the part that always sounds like cheating and isn't. On the 28th of February 2007, New Horizons flew past Jupiter. It did not stop there. It did not want anything from Jupiter except geometry. As it fell in toward the planet, Jupiter's gravity pulled it forward. As it swung around and out, the planet's gravity pulled it back. In the frame of reference of Jupiter alone, the spacecraft arrived and departed at the same speed, and nothing was gained. But Jupiter is not sitting still. Jupiter is moving around the Sun at about 13 kilometres a second, and the encounter was arranged so that the spacecraft left the encounter, travelling in more or less the same direction that Jupiter was already going. The result is that New Horizons stole a very small amount of Jupiter's orbital momentum. Roughly 4 kilometres per second was added to its speed relative to the Sun. Jupiter, in exchange, slowed down by an amount so small that it cannot be measured by any instrument that exists, and will not be noticeable for longer than the Sun has left to burn. The trade cost nothing, and bought about 3 years. But gravity assists have a price that is not paid in fuel. It is paid in scheduling. The alignment that lets you use a planet only exists when the planets are where they need to be, and the planets keep their own timetable and do not consult ours. If you're not ready when the window opens, you wait for the next one, and depending on the geometry, the next one may be a decade away, or several decades. The launch of New Horizons was pushed to the very start of 2006 specifically to catch a Jupiter alignment. Miss it, and the mission would have taken years longer, or gone somewhere else entirely, and the choice of which planet to visit is not free either. Voyager 2, 17 years earlier, had to make exactly this kind of trade at Neptune. To reach Triton, the mission deliberately flew the spacecraft only 4,950 kilometres over Neptune's North Pole, and the price of that geometry was that Neptune's gravity threw it steeply downward, out of the plane the planets orbit in, at about 48 degrees below it. It got Triton. It gave up any chance of a controlled path through the region we're heading for tonight. Every gravity assist is a bargain of that kind. You take the speed, and you accept the direction that comes with it. There is a third constraint, and this is the one people find hardest to accept, because it sounds like an oversight and it is actually a law. There are no brakes. Slowing down at your destination costs, roughly, the same enormous amount of energy that speeding up cost in the first place, and it has to be paid at the far end, which means you have to carry the propellant for it all the way out. That doubles the exponential. No outer solar system mission has ever been able to afford it. So New Horizons passed Pluto at 13.78 kilometres per second, and passed the next object at around 14, and will pass everything else at about the same speed, forever, until it leaves the solar system entirely. Think about what that means for a visit. A flyby of a body in the Kuiper belt does not last a day. The genuinely useful high-resolution part of it lasts minutes. You approach for years, you get a few minutes of good data, and then you are past it and receding, and there is no second attempt and no going back. The entire scientific yield of a decade of flight is collected in less time than it takes to boil a kettle twice, by a machine executing a sequence that was written and uploaded weeks earlier, and you have to have aimed correctly, not roughly correctly, correctly. From more than 4 billion miles away, at a target smaller than a city, with the aim locked in years before you arrive. We will come back to that, because aiming is going to turn out to be the entire problem, not the distance, not the cold, not the emptiness. But hold on to the shape of it for now. A single throw, made as hard as physics allows, corrected once by a planet's gravity, unable to stop, arriving at a destination it must have known about years in advance. That is how you get to the Kuiper belt. There is no other way that anyone has ever managed. Now comes the part that nobody puts in the diagrams either, and it is the part that occupies almost all of the actual journey. Because after the noise of that January afternoon and the brief geometry lesson at Jupiter, what happens next is 9.5 years in which absolutely nothing happens at all. And it turns out that surviving nothing is a harder engineering problem than surviving the launch. There is a version of space travel that television has taught all of us, in which the journey is a montage, and the interesting part is at either end. The real version has a different shape. In the real version, the journey is almost the entire thing, and it is made of waiting, and the waiting has to be engineered as carefully as the launch. New Horizons left Earth in 2006 and reached Pluto in the middle of 2015. That is 9.5 years, and for something like 1,873 days of it, a little over 5 years, spread across 18 separate stretches, the spacecraft was asleep. Hibernation, on a machine like this, is not a metaphor. Most of the systems are powered down, the instruments are off, the computer runs a minimal loop, the spacecraft spins slowly for stability, and once a week it sends a single beacon tone home, a signal that carries essentially no information except the one thing anyone wants to know, which is that it is still alive. Once a year, the team would wake it up for a checkout, run the instruments, exercise the systems, confirm that nothing had quietly failed in the dark, and then put it back to sleep. The reason for that is partly wear and partly people. Components that are switched off do not degrade the way components that are running do. But the larger reason is that a mission control team is not a machine, and asking a group of human beings to actively fly a spacecraft for 9.5 years, at full attention, waiting for something that will not happen for most of a career, is a good way to lose the people you will need on the day it matters. Hibernation was as much about protecting the humans as the hardware, and that is a real feature of distance that almost nobody thinks about. When you're dealing with the outer solar system, the relevant unit of time is not the year, it is the career. A person who joined the New Horizons team as a graduate student at launch was in their 40s by the Pluto flyby. Some of the engineers who built the instruments had retired before those instruments returned their most important data. There are people whose entire working lives are bounded by the two ends of one coasting trajectory. There is something else worth knowing about what was asleep out there, because it is the only genuinely human thing aboard. Tucked inside the spacecraft is a small container holding about 30 grams of ash. They belong to Clyde Tombaugh, the farm boy from Kansas who sat at a machine in Arizona in 1930, flicking back and forth between two photographic plates until he noticed a single point of light that had moved, and who thereby found Pluto. He died in 1997, 9 years before the launch. The result is that a man who discovered the 9th object on the old list is the only human being whose remains have ever left the planetary part of the solar system, and he is still going, at 14 kilometres a second, outbound. And one instrument never slept at all. On the outside of the spacecraft there is a thin plastic film panel, about 1,200 square centimetres in area, wired so that when a grain of dust strikes it hard enough to punch through, the impact registers as a tiny electrical pulse. It is called the Venetia Burney Student Dust Counter, named for the 11-year-old girl in Oxford who suggested the name Pluto in 1930, and it was built and is still operated by students at the University of Colorado. It is the only student-built instrument ever flown on a NASA planetary mission. It has been counting continuously since 2006. Hold on to it. Near the end of tonight, that panel is going to overturn the outer boundary of the solar system as it appears on every diagram ever printed. Now, the power. There is no sunlight worth having out here, so solar panels are not an option. At Pluto's distance, a panel that runs a house on Earth would struggle to run a small lamp. So New Horizons carries a radioisotope thermoelectric generator, a block of plutonium-238 that produces heat as it decays, wrapped in devices that turn part of that heat directly into electricity, with no moving parts at all. At Pluto, the whole generator was producing about 200 watts. Sit with that. 200 watts is a little more than 2 old household light bulbs. It is less than the power draw of a desktop computer. Of that 200, the instruments got roughly 28 watts between them, and the radio transmitter that has to reach across 4.5 light hours to a dish on Earth runs on about 12. Plutonium-238 has a half-life of just under 88 years, so the output falls by something like 1% or 2 every year. It has been falling since 2006. It will keep falling. We will come back to what that number reaches, and when, because it is the quiet clock running underneath this entire story. Then there is the data. This is the part that I find genuinely difficult to hold in my head, because it is so far from the way information moves in the rest of our lives. New Horizons collected around 50 gigabits of data at Pluto. In the currency most people use, that is somewhere around 6 gigabytes, a couple of high-definition films. It came home at between 1 and 2 kilobits per second. That is roughly the speed of a modem from the 1980s, operating across 4.5 light hours, with the signal arriving at Earth so faint that only the largest antennas on the planet can hear it at all. The Deep Space Network's 70-metre dishes, 3 of them, in California, in Spain, in Australia, positioned so that at least one always has the sky the spacecraft is in, are the only ears that work for this. The last of the Pluto data did not arrive until the 25th of October 2016. The encounter took a day. Reading the encounter took 15 months, and all of it is one way, in the sense that matters. At Pluto, the one-way light time was 4 hours and 25 minutes. Send a command, and the acknowledgement that it arrived comes back nearly 9 hours later. There is no steering. There is no reacting. There is no version of this where somebody at a console sees a problem and fixes it. Everything the spacecraft does at the far end, it does alone, executing a sequence that was written weeks earlier by people who had to imagine every circumstance in advance. Which is why the 4th of July 2015 is the worst day in the history of this mission, and one of the best arguments I know for why deep space is a psychological problem as much as a physical one. 10 days out from Pluto, with the encounter sequence being loaded, the main computer was asked to do 2 demanding things simultaneously: compress a large batch of data while receiving the flyby command sequence, and it overloaded. The spacecraft did exactly what it was designed to do. It recognized a fault, switched to its backup computer, went into safe mode, and turned its antenna toward Earth to ask for help. And then there was silence for 81 minutes. Not because anything was wrong for 81 minutes, because the signal saying something had gone wrong took 4.5 hours to arrive, and the question they sent back took 4.5 hours to reach the spacecraft, and the answer took 4.5 hours to come home. Every single exchange in the recovery was a 9-hour round trip. The team had 3 days to fix it before the encounter began, and they used almost all of them, and they got it back. About 30 planned observations were lost, but think about the room during those days. There is nothing you can do quickly. There is nothing you can do at all except send a carefully considered message into the dark, and then go and wait most of a working day to find out whether it helped, knowing that a decade of your life, and a billion-mile trajectory that cannot be repeated is sitting at the far end of that delay, and that the encounter window is closing at 14 kilometres a second and will not reopen. That is the texture of the crossing, not danger, not drama. Long, structured, disciplined waiting, punctuated by moments where the waiting becomes unbearable, and there is still nothing to do but wait. And out at the far end of all that patience, the spacecraft is falling through a region that we drew as a wall of rubble, and it is about to cross the line where the diagrams say the Kuiper belt begins. Here is what happens at that line. Nothing. Nothing whatsoever, and the reason nothing happens is going to tell us more about this place than any of the objects in it. At some point in 2015, on a date that nobody marked and no instrument recorded, New Horizons crossed 30 astronomical units from the Sun and entered the Kuiper belt. Nothing changed. No boundary was detected because there is nothing to detect. There is no wall of debris, no change in the density of anything, no shift in the magnetic environment, no marker of any kind. The spacecraft did not know. The team did not know, not to a specific day, because the question does not have that kind of answer. You are simply, at some point on the inside of a statistical description that you were previously on the outside of. I want to be careful with the phrasing here, because this is the first genuinely important idea tonight, and it is easy to say it and skate past it. The Kuiper belt is not a location, it is a probability distribution. It is the answer to the question, where do we tend to find these objects? And the answer is a broad, soft-edged, three-dimensional smear of likelihood that has no more physical presence than the phrase, the suburbs, has when you drive out of a city and cannot say which house was the last one. You cannot arrive at a probability. Hold on to that sentence. We will need it later, and it will be doing considerably heavier work by then. There is a related confusion worth clearing up now, because a lot of people carry it and it distorts the whole picture. The Kuiper belt is not the edge of the solar system. It is not even close. The heliosphere, the bubble of charged particles blown outward by the Sun, which is a real physical structure with a real measurable boundary, extends far past the belt. Voyager 1 crossed the outer edge of it, the heliopause, in August 2012 at about 121 astronomical units. Voyager 2 crossed it in November 2018 at about 119. Both of those crossings were detectable. The plasma density jumped, the magnetic field reoriented, the particle counts inverted. The instruments knew, and the scientists could point at a date and say that on that day, this spacecraft left the Sun's own atmosphere. That is a boundary. It is roughly 2.5 times further out than the far edge of the belt, and beyond it the Sun's gravitational reach continues for something like 100,000 astronomical units more, out through the Oort cloud, which we have talked about on this channel before and which makes the Kuiper belt look like a doorstep. So when the diagram shows the belt as the outer wall of the solar system, it is compressing something enormous into something tidy. The belt is not the edge. It is a densely populated shelf near the beginning of the outward journey, and everything past it is bigger. But there is structure inside the belt, and it is worth understanding what kind of structure it is, because it is not the kind you can see. The structure is resonant. It is made of arithmetic relationships between orbits, not of objects sitting in places. Consider Pluto, which is the most famous resident. Pluto orbits the Sun once every 248 years, and Neptune orbits once every 165. Divide one by the other, and you get 3:2. Pluto goes around twice for every 3 times Neptune does. That relationship is not a coincidence, and it is not fragile. It is a lock. Every time Pluto and Neptune approach the arrangement where they could interfere with each other, the timing works out such that they are far apart, and the pattern repeats, and it has repeated for billions of years. The effect of that lock is genuinely counterintuitive. Pluto's orbit is elliptical enough that for part of it, Pluto is closer to the Sun than Neptune is, most recently from the 7th of February, 1979 to the 11th of February, 1999, a stretch of 20 years during which the 9th planet, as it was then, was in fact the 8th. And in all that time the two bodies never came close to one another. They cannot. The resonance forbids it. Pluto is not alone in that lock. There is an entire population of objects sharing the 3:2 relationship with Neptune, and astronomers call them Plutinos. There are other resonances too, 2:1, 5:3, and more. These families are invisible in the sense that matters for a traveller. You could pass right through the 2-to-1 family and see nothing, because the family is not a place, it is a shared arithmetic. But they are the clearest fingerprint we have of something enormous that happened out here a very long time ago, and we will come back to what it was. While we are at the line that is not there, we should deal briefly with the argument that most people associate with this region, because it is the one thing about the Kuiper belt that everyone has an opinion about. In 2005, a team led by Michael Brown found an object out here that turned out to be slightly more massive than Pluto. It was eventually named Eris, and Eris created a problem that had been coming for years. If Pluto is a planet and Eris is bigger, then Eris is a planet, and so, in time, are the next 10 or 20 things anyone finds out here, because there is no natural gap in the sizes. In August 2006, the International Astronomical Union voted on a definition, and under that definition Pluto was reclassified as a dwarf planet, and a great many people took it personally. I do not want to relitigate that argument tonight, and I have no interest in telling you which side is right. But there is something in it that matters for where we are going. What the fight was really about was the discovery that the solar system does not sort itself into the categories we were taught. We inherited a list of 9 things, and we assumed the list described a natural kind. It did not. It described the limits of a telescope. Between Pluto's discovery in 1930 and the summer of 1992, the total known population of everything beyond Neptune was 2 objects, Pluto and its large moon Charon, and that was not because there were 2. It was because we could see 2. Then, in August 1992, after a 5-year search, David Jewett and Jane Liu found a faint moving point of light that turned out to be an object about 160 kilometres across, orbiting out past Neptune. They catalogued it as 1992 QB1. It was eventually named Albion. It was the 3rd thing anyone had ever found out there. There is an irony buried in the name too. The belt is named for Gerard Kuiper, a Dutch-American astronomer who argued in 1951 that a disk of small icy bodies should have formed out past Neptune. That much was right. But Kuiper then argued that the disk would not still be there, because he believed Pluto to be roughly the size of the Earth, and a body that size would have swept the region clear over the age of the solar system. So the man the belt is named after predicted the belt and then predicted its absence, on the strength of a mass estimate for Pluto that turned out to be wrong by a factor of several hundred. An Irish astronomer, Kenneth Edgeworth, had floated a similar idea in the 1940s and reached a less pessimistic conclusion, which is why some astronomers insist on calling it the Edgeworth-Kuiper belt, and why a few argue that neither man really predicted what was actually found. Today the catalogue holds more than 3,000, and the estimated population above 100 kilometres in diameter is more than 100,000, which means that essentially everything we know about this entire region of the solar system has been learned inside a single human lifetime, and most of it inside 30 years. The map you were shown at school was not simplified. In the parts that count, it was blank, and somebody drew on it anyway. It is worth sitting with how recent all of this is. If you are over 40, the Kuiper belt was a hypothesis when you were born and a confirmed population before you finished school. If you are over 60, you were taught a solar system in which everything past Neptune was one small planet, and a great deal of nothing. Neither of those was a lie. They were simply the honest limits of what could be seen at the time, presented with a confidence that the evidence did not support, which is a pattern we are going to run into again tonight, more than once, and each time it will be about something further out. So we are inside now. We have crossed a line that does not exist, into a region that is not a place, past a boundary that is not the edge, in a solar system that turned out not to have the shape we were given. And we still have not looked out of the window. That comes next. And the light out here is the first thing tonight that is going to genuinely surprise you, because almost everything you assume about it is wrong in the same direction. Ask almost anyone what the Kuiper belt looks like, and they will say the same word: black. A black void, with a spacecraft in it, and somewhere impossibly far behind, a small pale star that used to be the sun. That answer comes from arithmetic that is correct, and an intuition about the arithmetic that is not. The correct part first. Light spreads out as it travels, and the amount falling on any given surface drops with the square of the distance. Double your distance and you get a quarter of the light. So at 30 astronomical units, where the belt begins, the Sun delivers about 1/900th of what it delivers at Earth. At 40, 1/1600th. At 50, 1/2500th. Now 1/1600th sounds like nothing. It is not nothing. Full daylight on Earth on a clear day runs to something over 100,000 lux. That is the unit for how much light is actually landing on a surface. 1/1600th of that is around 60 lux. 60 lux is the lighting in a stairwell. It is the light in a corridor at the back of a building. It is a little dimmer than the light most people read under, and considerably brighter than a restaurant that is trying to be atmospheric. At 60 lux you can see your hands clearly. You can read a headline. You can tell the difference between a red car and a blue one, though the colours will be tired and low. You would not describe a room at 60 lux as dark. You would describe it as badly lit. There is a way to check this for yourself, and I recommend it, because it is the rare piece of astronomy you can verify from a doorstep. NASA formalized it, and gave it a name, Pluto time. On any given day, at a given place on Earth, there is a moment shortly after sunset, and another shortly before sunrise, when the illumination where you're standing exactly matches the illumination at Pluto's surface at local noon. Go out at that moment and look around. The trees are still trees, the road is still a road, the colour has drained out of everything, and the world has gone quiet in that particular way it does at the end of the day, but you can see perfectly well. That is high noon in the Kuiper belt, and from out there, the sun is still about 250 times brighter than a full moon is here. If you have ever walked home across open ground under a full moon and been surprised at how much you could see, multiply that by 250, and you have the daylight of the outer solar system, so it is not dark. But this is the part where it gets genuinely strange, because what is different out there is not the quantity of the light, it is the shape of it. Let me put you somewhere. You are standing on a surface at 40 astronomical units from the sun. It is local noon. The ground under you is water ice with the mechanical properties of granite, because at 40 Kelvin ice does not behave like anything you have handled. It is not white. It is a dull, dark red-brown, the colour of dried blood or old brick, stained that way by 4.5 billion years of ultraviolet light and cosmic rays working on simple organic molecules. The light is exactly what we said. The last few minutes of twilight, holding steady with no sense that it's about to fade. Your hands are visible, your suit is visible, there is enough light to work by. Now look up. The sun is directly overhead, and it is a point, not a small disk, a point. From Earth the sun is 1/2 degree across, about the width of your little fingernail at arm's length. From here it is about 45 arcseconds, which is under a 50th of that, and 45 arcseconds is smaller than the resolving limit of the human eye. Your eye cannot make it into a shape. It is a single, brilliant, dimensionless spark, so bright it hurts to look at directly, and so small it has no more geometry than a star. Look at the shadow you're casting. It has an edge like a cut. On Earth, every shadow edge is soft, because the sun is a disk and light arrives from slightly different angles across it, so there is always a fuzzy border between full shadow and full light, roughly a centimetre of softness for every metre of height. Out here, the source has no width, so there is no soft border. Your shadow is a hole in the light with a boundary sharper than anything you have ever seen a natural shadow make. And inside that hole it is genuinely, absolutely dark, because there is no air to scatter light into it and nothing overhead to bounce any back. And now the part that most people, when they picture this, get exactly backwards. Look at the rest of the sky. It is black, not dark blue, not dusky, not the dark indigo of high altitude on Earth. It is black, and it is absolutely full of stars, and they are all there, at noon, in the daytime, surrounding that vicious little spark of sunlight. Because a sky's only bright when there is an atmosphere thick enough to scatter sunlight across it, and there isn't one. So the stars never go out. Sunrise, if you can even call it that, would not wash them away. There is no dawn, there is no golden hour, there is no colour in the sky at all, ever, because there is no sky, only the direct line between you and whatever is out there. Stand in that for a moment. A landscape lit like a stairwell, a shadow with a razor edge, a blinding point overhead, and behind it, undimmed, the whole star field, permanently. That combination does not occur anywhere in human experience, and it is not what any of us picture. We picture darkness because we think of cold and distance, and we translate them into black. The truth is more unsettling than black, because black is simple. This is a bright day underneath a night sky, and there is no arrangement of earthly weather or time or place that produces it. There is a second thing that follows from the same fact, and it has been quietly useful to science. Because the sky out there really is empty of scattered light, New Horizons has been able to do something no telescope near Earth can. Close to the Sun, we sit inside a faint haze of dust in the plane of the planets, which scatters sunlight and puts a floor under how dark any measurement can be. Out past Pluto, that haze thins away almost to nothing. So the mission has used its long-range camera to make one of the cleanest measurements ever attempted of the cosmic optical background, the total accumulated glow of every source in the universe outside our own galaxy. It is a strange kind of privilege. The only way to properly see how dark the universe is was to go somewhere that dark first. The cold, while we are here, is worth stating precisely, because people usually reach for the word cold and stop there. Pluto's surface averages around 44 Kelvin, ranging from about 33 to 55 depending on where and when you measure. That is roughly minus 229 degrees Celsius. Arakoth, further out and darker, sits somewhere around 30 to 40 Kelvin. At those temperatures, the words do not mean what you expect. Water ice is not slippery. It is a structural material, harder than most rock, and it forms mountains that hold their shape for billions of years. Nitrogen, which you are breathing right now, is a solid you could quarry. Methane is a mineral, and chemistry, in the ordinary sense, essentially stops. Reactions that take seconds in a warm laboratory take longer than the age of the solar system out here. That is precisely why the region matters, and we will come back to it, because a place where nothing can react is a place where nothing gets erased. If you turned around and looked for Earth, incidentally, you would fail. Earth is 1 astronomical unit from the Sun, and you are 40. From here, the two of them are never more than about 1.5 degrees apart in the sky, and Earth is a faint blue-green speck sitting right next to something so bright it has effectively erased the region around it. New Horizons managed to photograph the Earth from beyond Pluto only by using the spacecraft's body to block the glare. To an eye, there is nothing there. That is what you would see, and I want to flag something, because we are going to need it much later tonight. The light out here has been like this for 4.5 billion years, and it will be like this for billions more. The sun will keep delivering its 60 lux to these surfaces long after everyone listening to this is gone. Nothing out here is going dark. Twilight, not darkness. Remember that. Now that we can see, the obvious question is what there is to look at. And this is where the journey turns, because the answer is going to be nothing. And the reason for the nothing is the most important number in this entire video. Let us do the arithmetic properly, because everything from here on depends on it. We're inside a shell that runs from 30 astronomical units to 50. To find the volume of that shell, you take the volume of a sphere 50 astronomical units in radius and subtract the volume of a sphere 30 astronomical units in radius. The numbers come out around 450,000 cubic astronomical units. Even if you flatten the shell considerably to account for the fact that most of these objects orbit near a plane rather than filling a sphere, you are still left with something in the range of tens of thousands of cubic astronomical units of room. Now put the population in. The best estimates give us more than 100,000 bodies larger than 100 kilometres across, and a much larger, poorly constrained number of smaller ones. Divide one by the other, and you get roughly 100-kilometre or larger object per cubic astronomical unit. I want to make that number physical, because in units it slides past. A cubic astronomical unit is a box 150 million kilometres on each edge. The Earth is 12,742 kilometres across, so you could line up nearly 12,000 Earths along one edge of that box. You could fit the entire orbit of Venus inside it and have room left over. And somewhere in that box, you do not get to say where, there is one object roughly the size of Wales, or Vermont, or Sicily. That is the crowding. That is the wall of rubble. If you were set down at a random point inside the Kuiper belt and told to find the nearest object bigger than 100 kilometres, it would typically be tens of millions of kilometres away. At that range, a 200-kilometre body reflecting a few percent of 1/1600th of daylight is not merely hard to see. It is fainter than the faintest star your eye can register, by a wide margin. It is not there as far as you're concerned. The dust agrees. Along the paths the voyagers flew, between 30 and 60 astronomical units, the the measured density of detectable dust grains came out at something on the order of 2 × 10 to the -8 per cubic metre. Let me translate that. It means roughly 1 grain of dust in every 50 million cubic metres of space. 50 million cubic metres is a cube nearly 400 metres on a side. Picture a cube the height of a skyscraper in all 3 directions containing 1 speck. The student dust counter on New Horizons, that plastic panel built by university students, has been reading levels higher than the models predicted, and that discrepancy is going to become extremely important later tonight. But note what higher than predicted means here. It means an environment that is still emptier than the best vacuum chamber ever built on Earth by a substantial margin. The Kuiper belt is a better vacuum than anything we can manufacture, which is why the hazard never materialized and never was going to. Every single spacecraft that has crossed the asteroid belt, Pioneer 10 and 11, both Voyagers, Galileo, Ulysses, Cassini, Dawn, Juno, New Horizons, has crossed it without hitting anything of substance. Not one of them has been damaged by an asteroid. Not one has needed to dodge. When Pioneer 10 went through in 1972, there was genuine concern in some quarters that it might not survive, and that concern was reasonable given what was known at the time, and it was completely misplaced. The same is true out here, more so, because the Kuiper belt spreads a comparable count of objects through a volume many thousands of times larger. It is worth having the inner solar system comparison in hand, because it is the one most people have a feel for. If you take the couple of million asteroids in the main belt that are a mile across or larger and distribute them honestly through the volume they occupy, the average separation between them comes out around 3 million kilometres. That is roughly 8 times the distance from here to the Moon. If you were standing on one of those asteroids, the nearest other one would be so far away that you would need a telescope to find it, and you would probably need to be told where to look. That is the crowded belt. The Kuiper belt takes a similar count of objects and spreads them through a volume thousands of times larger again. There is one more wrinkle that makes it emptier still, and it is the vertical dimension. Diagrams draw belts flat, and part of this one genuinely is flat. A population on nearly circular orbits, all lying close to the same plane. But there is a second population out here on orbits tilted by tens of degrees, which means those objects spend most of their time far above or below the plane, sweeping through an enormous additional volume of space that the flat diagram does not even acknowledge. Adding that tilted population does not make the region more crowded. It makes it thinner, because you are putting the same objects into a much thicker slab. And a final note on the dust, because it is not all local. Some of the grains hitting that plastic panel did not come from the Kuiper belt at all. They came from outside the solar system entirely. Streams of interstellar dust drifting through from the surrounding galaxy, passing through our system the way weather passes through a valley. Which means the belt's dust environment is a mixture. Local debris from collisions between objects too faint for us to see, and material that has been travelling between the stars. Sorting one from the other is genuinely difficult, and it is part of why the excess readings have taken years to interpret. So the danger you were promised does not exist, and now, having taken that away, I have to give you what replaces it, and I think it is worse. Suppose you did it. Suppose the propulsion problem is solved, the life support works, the crew survives the crossing, and you arrive. You choose a point at random inside the belt, not near any catalogued object, just somewhere in the middle of the population, and you stop. You look out. Behind you there is a single brilliant point of light, no bigger than a star, which is the sun. In every other direction there is complete blackness, thick with stars, and those stars are in exactly the same positions they occupy from Earth, because you have not gone anywhere in a stellar sense. Nothing is closer. Nothing is further. The constellations are the constellations, and that is all. There is no horizon, because there is no ground. There is no landmark, because there is nothing near enough to be a landmark. There is no motion, because everything is either too far away to show motion or too small to see. If you sat at that window for a year, nothing you could see with your own eyes would change. Your instruments would tell you that you had arrived. Your navigation computer would confirm your position to within a few thousand kilometres, and it would state correctly that you were inside the Kuiper belt, and your eyes would report, also correctly, that you were nowhere at all. That is the mismatch, and I think it is the strangest thing about this entire region. Every other destination human beings have imagined has a there. A mountain has a summit. You stand on it, and you know. A pole has a point. You plant something in it. The moon has a surface and the moment of arrival is unmistakable. The dust comes up around the landing gear. Mars has a horizon and a sky the wrong colour. Even the middle of an ocean, which is the emptiest thing on this planet, has a surface and a swell and a change in the light. The Kuiper belt has none of that. It is the first destination in the history of human ambition that a person could arrive at and be entirely unable to verify by any human sense. You cannot see it. You cannot feel it. There is no moment. There is no arriving. There is only a computer telling you that the statistical description you are aiming for now includes your position. You cannot arrive at a probability. I said it earlier and it sounded like a turn of phrase. It is not. It is the literal operational truth about this region, and it has consequences that we will spend the rest of tonight unpacking. And here is the first of them, which I want to plant now. If arriving in the belt means nothing, then the only meaningful destination out here is a specific object, not the region. A thing, a named, catalogued individual body whose position you know well enough to steer at, years in advance from 4 billion miles away, at 14 kilometres a second, with no ability to slow down. That is a different problem entirely from the one everyone thinks this is. The problem is not distance. Distance is expensive and slow, but it is understood. You buy it with a large rocket and a great deal of patience. The problem is that after you have paid for all that distance, you arrive in an enormous volume of nothing, and unless you already knew exactly which grain of the dark to aim at before you left, the journey has brought you precisely nothing at all. Hold that. In about an hour it is going to close around the whole video. But before that, we should go and look at what happens when the aiming does work. Because it has worked. Twice. And the second time it worked, a spacecraft flew past an object 35 kilometres long at a distance of 3,500 kilometres after a course correction planned years in advance, and photographed the single most valuable thing anybody has ever found in the outer solar system. It does not look like much. It looks like two lumps stuck together, and it is a photograph of the moment before the planets existed. The target had to be found before it could be aimed at, and finding it very nearly did not happen. After the Pluto encounter, New Horizons had a small amount of manoeuvring fuel left, and a narrow cone of space it could still reach. Anything outside that cone was unreachable no matter how interesting. So from 2011 onward, the team ran ground-based searches with some of the largest telescopes on Earth, looking for anything at all in the right place. They found nothing usable. The problem was the background. The spacecraft's path happens to run toward the direction of the centre of our galaxy, which is the single most crowded patch of sky there is. Looking for a faint, slow-moving speck against the star fields of the galactic centre is like looking for one particular grain of salt scattered on a page of newsprint. In the end, they had to leave the ground. In June 2014, the Hubble Space Telescope found a target, a faint moving point, catalogued as 2014 MU69 and later named Arakoth, from a Powhatan word meaning sky. It sits at about 44 astronomical units, on an almost circular orbit tilted barely at all, taking around 298 years to go around once. Even then, the position was not known precisely enough to aim at. So in 2017, teams went out to watch it pass in front of stars. That technique, waiting for a distant object to blink out a star for a fraction of a second, is the highest precision tool we have for bodies we cannot photograph, and it requires being in exactly the right narrow track on the Earth's surface at exactly the right moment. Telescopes were driven into the field in Argentina. An airborne observatory flew over the Pacific. From a handful of milliseconds of starlight going missing, the object's size and position were pinned down well enough to steer at. Then they steered at it and waited another 18 months. It is just before dawn, universal time, on the 1st of January 2019. 4 billion miles from Earth, a spacecraft the size of a grand piano is closing on an object 35 kilometres long at 14 kilometres per second, and there is nobody flying it. The encounter sequence was uploaded weeks ago. Everything that is about to happen, every camera pointing, every instrument setting, every rotation of the spacecraft to keep the target in frame, was written by people on Earth who had to anticipate every circumstance in advance and then let go. The one-way light time is over 6 hours. Nothing can be corrected. Nothing can be checked. The spacecraft is entirely alone with the task it has been carrying, unopened, for a year and a half. Closest approach comes at 3,500 kilometres. The useful high-resolution window is a matter of minutes, The object crosses the field, gets photographed at a range where 35 kilometres actually fills a frame, and then it is behind and receding and gone forever. At no point does anyone on Earth know whether it worked. And then the wait. 6.5 hours of nothing while the confirmation signal crawls in. In a control room in Maryland, people who have given a decade or more to this stand around and watch a screen, and there is no useful thing any of them can do, because the entire outcome was decided while they were asleep, and the news is still in transit. When the carrier tone finally comes through, a machine 4 billion miles away, reporting that it is healthy and has data on board, the room does what rooms do, and then everyone has to wait most of another year for the pictures to actually arrive down a 1 kilobit line. What came back is, I think, the most important photograph ever taken in the outer solar system, and it looks like almost nothing. It looks like two lumps stuck together. A larger, oddly flattened lobe, more like a discus than a ball, joined to a smaller, rounder one, meeting at a distinct narrow neck. The whole thing about 35 kilometres from end to end and coloured a dull, dark red. That is the object. Now here is why it matters. Arikoth is what is called a contact binary. Two separate bodies that came together and stayed together, and everything about the way they came together is wrong for the story most of us were taught about how planets form. The story we were taught is a story of violence. Dust sticks to dust, pebbles collide and merge, small rocks smash into each other, and the survivors get bigger, and after millions of years of demolition you have planets. Growth by surviving impacts. Arikoth did not do that. Look at where the two lobes meet. The neck is intact. Neither lobe is deformed at the join. No flattening, no shattering, no crater, no debris field. Both bodies retain their shapes as though they had been set down against each other by hand. Model the geometry, and you get a closing speed of a few meters per second at most. A few meters per second. That is walking pace. That is the speed of somebody crossing a room. Two objects, each the size of a small city, drifted together at the speed of a person walking 4.5 billion years ago and came to rest against one another. And they are still touching. Nothing has separated them. Nothing has hit them hard enough to matter. No planet has passed close enough to pull them apart. In 4.5 billion years, a period during which the Earth formed, was struck by something the size of Mars, cooled, grew oceans, invented life, froze over more than once, and rebuilt its entire surface many times over. The two lobes of Arikoth have simply remained in contact. The scientific weight of that is enormous, because it settles an argument. There has been a long-running competition between two pictures of how planet formation gets started. The violent picture, Collide and Survive, has a well-known problem. At the relevant sizes and speeds, colliding particles tend to bounce off each other or shatter rather than stick, and it is genuinely hard to get past that barrier. The alternative picture says that growth does not begin with collisions at all. It says that in a disk of gas and dust, drifting solid particles can concentrate themselves aerodynamically into a dense clump, and if the clump gets dense enough, its own gravity takes over and it collapses, straight from a cloud of pebbles to a body tens of kilometres across, in one step, without any high-energy impacts at all. And if the collapsing cloud is spinning too fast to make a single object, it makes two, already orbiting each other, already moving slowly relative to one another. Arikoth is that process, stopped. Not a fragment of something bigger, not the survivor of a demolition, the intermediate step preserved, with the two pieces resting where they landed, even its shape supports it. The larger lobe is remarkably flat, and that flatness now looks like a signature of exactly this kind of formation, the collapse of a rotating cloud producing a discus rather than a sphere. The surface tells the same story of being left alone. Arikoth is intensely red, coloured by organic molecules processed by billions of years of radiation. Spectroscopy found methanol ice and complex organics on the surface, and did not find water ice, which was a real surprise for an object everyone expected to be a dirty snowball, and which probably means the water is buried under a processed crust rather than absent. And there are very few craters, almost none. A surface that has been sitting in one of the emptiest volumes in the solar system, being hit by essentially nothing for the age of the solar system. Its orbit says the same thing in a different language. Arikoth goes around the Sun on a path that is very nearly a circle, tilted by almost nothing relative to the plane the planets orbit in. That combination is not an accident, and it is not common. An object that has been thrown by a planet carries the evidence of the throw permanently, in the form of an eccentric or a tilted orbit. Orbits do not settle back down on their own out here, because there is nothing to settle them. A circular, uninclined orbit at 44 astronomical units is therefore a statement. This object has never been thrown. It formed roughly where it is, and it has been going round quietly ever since. It is also one of the coldest things ever photographed up close, somewhere around 30 to 40 Kelvin. At that temperature nothing changes, nothing evaporates, nothing reacts, nothing flows, which is precisely why it is still there in its original condition, and why we can read it at all. I called it the most valuable object in the outer solar system, and I meant it literally. Everything else we can study has been altered. Every planet melted and separated into layers and destroyed its own construction record. The Moon and Mars keep more of theirs, but both were shock processed by heavy bombardment. Comets come from out here but arrive cooked, having been heated repeatedly by close passes to the Sun. Meteorites are fragments, torn out of context, that have survived being hit and then survived falling through an atmosphere. Arikoth is the intact original. 2 pieces of the material the solar system was assembled from, in the configuration they assumed on the day of assembly, at the temperature they have been at ever since, in the orbit where they were made. And we have looked at it for a few minutes once in passing, at 14 kilometres a second. The data itself took more than a year to arrive. The highest resolution frames, the ones that show the neck clearly, the ones that made the gentle merger argument possible, did not reach Earth until well into 2020. There is something appropriate about that. An object that has not changed in 4.5 billion years, revealing itself over 18 months, 1 kilobit at a time, to a species that has been able to see it at all for about a decade. That flyby is the most distant close encounter with any object in history, and it stands as the second and final time in the history of our species that we have seen a Kuiper belt object from close range. Here is the thing that turns this from a curiosity into a discovery. Arikoth is not unique. It belongs to a specific population out there, and that population has a property that, once you understand it, tells you something about the last 4.5 billion years that no photograph could. The objects out here sort themselves into families, and the families are defined not by what the objects are made of, but by what has happened to them. There is a population locked into resonances with Neptune, the Plutonos and their relatives, and their locks are the fingerprints of having been captured. There is a scattered population on long-stretched tilted orbits that reach far beyond the classical belt, and their orbits are the fingerprints of having been thrown hard and having survived it. There is a hot classical population sitting at similar distances to the quiet objects but tilted by tens of degrees, and those tilts are the fingerprints of having been moved from somewhere else. And then there is one family with no fingerprints on it at all. They are called the cold classicals. They occupy a band roughly between 42 and 47 astronomical units, on orbits that are very nearly circular and tilted by almost nothing. The word cold here has nothing to do with temperature. Everything out there is cold. It means dynamically cold. Orbits with low eccentricity and low inclination. Orbits that have never been stirred. They are the only population in the outer solar system that is still where it formed. That claim needs justifying, and the justification is one of the most satisfying pieces of reasoning in planetary science, because it does not depend on a model. It depends on a fact about fragility. At least 1 in 5 of the cold classicals is a binary, not an object with a small moon. 2 comparable bodies, often nearly the same size, orbiting a common centre of mass. Some analyses put the fraction considerably higher than 1 in 5, and some researchers suspect that nearly all of them may have formed as pairs, with the ones we see as single objects being the ones whose partners were eventually lost or merged, and a great many of those pairs are wide. Wide meaning the 2 bodies are separated by thousands of kilometres, sometimes tens of thousands, taking months or years to circle one another. At those separations, each body holds onto its partner by the faintest thread of gravity you can imagine. These are objects perhaps 100 kilometres across, with surface gravity so weak you could jump off them, holding each other across a gap wider than the Earth. A pair like that is easy to break. Any close pass by a planet would strip them apart permanently. A moderate collision would do it. Any significant scattering event, the kind that produced the entire scattered disk, would separate them and send the 2 halves off on different paths, never to meet again. They have not been broken, which means, and this is the part I want you to sit with, that in 4.5 billion years nothing has come close enough to break them. Not a planet, not a large impact, not a scattering event, not one single encounter in the entire history of the solar system energetic enough to separate two objects held together by essentially nothing. That is not a sentimental observation, it is evidence, and it is the strongest evidence we have that these objects have been sitting in place, undisturbed, since the beginning. The pairs are intact, therefore the history was empty. The fragility of the binaries is the measurement. Think about what has happened everywhere else in that same span. The Earth was struck by something the size of Mars and threw off a moon. The inner solar system went through a period of bombardment intense enough to reshape every surface in it. Neptune moved. Uranus was knocked over onto its side. Jupiter and Saturn rearranged the outer solar system between them and flung a mass of material equivalent to many Earths out into the dark. It was, by any measure, a violent 4.5 billion years, and out at 44 astronomical units, two objects have been slowly circling each other through all of it, through the formation of the moon, through the origin of life on this planet, through every extinction, every ice age, every continent, through the entire history of everything you have ever heard of, circling at a few meters per second, unbothered. Nothing has ever come close enough to interrupt them. It is worth imagining what visiting one would actually be like, because the numbers make it stranger than it sounds. Put yourself on the surface of one member of a wide pair. The gravity is so weak that a firm push with your legs would send you off the surface permanently, so you would move by pulling yourself along carefully, like someone climbing in the dark. The horizon is close. A body 100 kilometres across curves away sharply, and you can see the edge of the world from anywhere on it. And hanging in that black star-filled sky, not moving, or moving so slowly you would need to watch for hours to be sure, there is another world exactly like the one you are standing on. Same size, same colour, same silence. It has been there, in that position, since before there was an Earth to look up from. The mechanism that made them is now reasonably well understood, and it is the same one Arakoth points to. In the disk of gas and dust the Sun formed from, small solid particles do not simply stick together into planets, because at the relevant sizes and speeds collisions tend to bounce or fragment. But solid particles moving through gas can concentrate themselves. Under the right conditions, a drifting swarm of pebbles can bunch up, and the bunching feeds itself, until the local density is high enough that the swarm's own gravity takes over and it collapses. That is called the streaming instability, and its output is not a slowly grown rock. It is a body tens or hundreds of kilometres across, made in a single collapse, and if the collapsing cloud carries more spin than a single object can hold, it does not make one body, it makes two, in orbit around each other, already slow, already close. The cold classical Kuiper belt is where the products of that process were never cleaned up. Everywhere closer in, the growing planets swept up the planetesimals or scattered them. Out here, at low density, in a region Neptune's migration never quite reached, they were simply left. The binaries are the direct evidence, and the fact that we can still see them, in pairs, is the reason we can say with confidence what the first step of planet formation actually looked like. There are other things worth knowing about this family. They are red, more uniformly red than any other population out there, and the redness appears to be a chemical signature of where in the disk they formed, which makes colour into a kind of birth certificate. They are small. Detailed surveys find that the population essentially stops producing large bodies above a few 100 kilometres, tailing off far more sharply than a simple grinding process would predict. And they are concentrated, with a noticeable clump of orbits near 44 astronomical units that has its own name, the kernel, and which is usually explained by Neptune's outward migration having proceeded in a jump rather than smoothly. And this has consequences well beyond our own solar system. The streaming instability was, for a long time, a theoretical proposal, an elegant way around a problem that had bothered planet formation modelers for decades, but one without direct physical confirmation. What the Kuiper belt has provided is confirmation you can photograph. Arakoth's gentle join and the cold classical binaries are two independent lines of evidence pointing at the same mechanism, and that mechanism is presumably what has happened around every other star with a disk of gas and dust, which is to say most of them. The way the first solid bodies got made here is very likely the way they got made everywhere, and the only place the evidence survived is a region we spent most of the 20th century believing was empty. I should also be honest about the edges of the argument, because there is a live disagreement. A study published in 2024 argued that the very widest binaries out there may not be primordial after all, and could have been assembled more recently by other means. That does not touch the main claim, which rests on the general population rather than the extremes, but it is a reminder that this field is very young and that the objects doing the arguing are faint points of light at the limit of what our instruments can resolve. There is one more thing the colours do, and it is a small piece of detective work I find genuinely satisfying. The cold classicals are red. The scattered and resonant populations, which sit at similar distances now, are on average much less red. If all of these objects had formed where they currently are, they should look alike, because they would have been made from the same material at the same temperature. They do not look alike. So the differences in colour are a record of different birthplaces, objects that formed closer to the Sun, where certain ices could not survive, ending up with a different chemistry from objects that formed further out. Which means that when Neptune migrated outward and dragged a population of objects along with it, it left behind a colour-coded record of who came from where. The belt is not just a population, it is a stratigraphy, and the strata are wavelengths. Here is where this leaves us on our journey. We came looking for the terror in a trip to the Kuiper belt, and we have not found it in the crossing, and we have not found it in the arrival, and we have certainly not found it here. Because what is out here is not menacing. It is undisturbed. It is the quietest place we know of. But quiet is not the same as inert, and I have been giving you a slightly incomplete picture. Because while the small objects have been holding perfectly still, some of the larger ones have been doing things that, according to the physics we brought with us, they should not be able to do at all. We have never sent a spacecraft to any of the objects in this part. We have never photographed their surfaces. Everything I am about to tell you was learned by watching stars go out. The technique is called stellar occultation, and it is beautifully simple. A distant object out in the belt passes in front of a background star. From the right narrow track on the Earth's surface, the star blinks off for a fraction of a second and comes back. Time that blink precisely, from several telescopes at different places, and you can reconstruct the shape and size of the thing that caused it, to a precision that no image could match at that distance. It is the only way we have to measure these bodies properly, and it requires knowing where the shadow will fall to within a few kilometres, weeks in advance, and then having equipment inside it when it does. That technique is how we found out that the outer solar system does not obey the rules we brought with us. Start with Quaoar. It is a body about 555 kilometres in radius, orbiting at around 43 astronomical units, with a small moon called Waywot about 80 kilometres across. It was found in 2002 by Chad Trujillo and Michael Brown, and at the time it was the largest thing anybody had found in the solar system since Pluto. Between 2018 and 2021, several occultation campaigns watched Quaoar cross in front of stars using ground telescopes and also the European Space Agency's CHEOPS satellite, and the light curves showed something nobody had ordered. Alongside the main dip from the body itself, there were additional brief dips, symmetric on either side. Quaoar has a ring. That by itself would be interesting. Where the ring is a problem. Every planetary system with a dense ring, Saturn, Jupiter, Uranus, Neptune, has that ring close in, inside a boundary called the Roche limit. The Roche limit is where a parent body's tidal forces are strong enough to overcome the self-gravity of anything trying to clump together. Inside it, material that tries to gather into a moon gets pulled apart faster than it can assemble, so it stays as a ring. Outside it, tidal shear is too weak to prevent accretion, so any ring material should gather itself into a moon in a geologically trivial amount of time. Decades, in some estimates. Quaoar's ring sits at about 7.4 times the body's radius. That is far outside its classical Roche limit. It should not exist. It should have become a small moon a very long time ago, and it has not. The result was published in Nature in February 2023, and the leading explanation is elegant and slightly humbling. Whether ring particles clump together depends not only on tidal forces but on how they collide, specifically on how elastic those collisions are. Ring particles out here are very cold ice, and very cold ice bounces. If collisions are elastic enough, the particles keep scattering off one another instead of sticking, and a ring can remain a ring in a place where the textbook says it cannot. So a rule we had treated as structural turns out to be conditional. It was never a law about distance. It was a law about distance under the assumptions we happened to have tested it under, all of which came from the warm inner solar system. And Kuiper is not alone in this. In 2013, a much smaller body called Chariklo, one of the Centaurs, the objects on unstable orbits between Jupiter and Neptune, turned out to have rings, which was the first time anything smaller than a giant planet had been found with any. Chiron, another Centaur, appears to have ring material too, and the amount of it seems to change over time. 10 years ago, rings around small icy bodies would have been considered an exotic curiosity. Now they look ordinary, and the question has quietly reversed. Not why do these few objects have rings, but how many of the others do, and how would we know? Then there is Haumea, and Haumea is not obeying anything. Let me put you there for a moment, because the numbers do not land otherwise. You are standing on Haumea. The first thing you notice is that the stars are moving, not slowly, in the way you would need patience to detect, visibly, the way clouds move on a windy day. Haumea rotates once every 3 hours and 54 minutes, which makes it the fastest spinning body of any significant size known in the solar system. Nothing else larger than 100 kilometres comes close. The whole star field wheels overhead while you watch, and a day here begins and ends before you would finish a long meal. The second thing you notice is the ground. It is not the ground of a round world. Haumea has been spun so hard for so long that it has been pulled out of shape, stretched into an elongated form roughly twice as long as it is wide. So the horizon does not curve away evenly. Face along the long axis, and the surface stretches out ahead of you, falling away gently. Turn 90 degrees and the world drops off sharply, much closer than it should. You're standing on something being held together against a spin that is very nearly fast enough to take it apart. Look up. There is a thin ring overhead discovered on the 21st of January 2017, when 12 telescopes at 10 European observatories watched Haumea pass in front of a star, and the light dipped more times than it should have. And out beyond it, 2 moons. Now the part that makes the whole scene make sense. The moons are made of the same material you're standing on. So is a scattered set of other icy bodies out in the belt, spread across a range of orbits, all sharing an unusual spectrum. They are the only confirmed collisional family in the outer solar system. A very long time ago, something struck Haumea hard enough to tear a substantial amount of material off it, spin it up to that ferocious rate, and leave the fragments to disperse. Everything you can see from that surface is the aftermath of a single impact. The spin, the shape, the ring, the moons, and a scatter of pieces spread across the region. And the spin has not slowed appreciably in the billions of years since, because there is nothing out here to slow it with. And then there are Eris and Make, which close the argument by attacking the assumption underneath all of it. Eris is the object that started the fight about Pluto. Found in 2005 by Brown, Trujillo and Rabinowitz, it is slightly smaller than Pluto in diameter and about 27% more massive, which makes it noticeably denser and rockier. Make is a little smaller and also bright and also covered in methane ice. Beginning in 2023, the James Webb Space Telescope did something on these surfaces that had never been possible before. It measured isotopes. Not just what molecules are present, but which versions of them. How much of the methane contains a deuterium atom instead of ordinary hydrogen, and how much contains carbon-13 instead of carbon-12. Those ratios are a chemical fingerprint of where and how a molecule was made. The measured deuterium to hydrogen ratios came out at about 2.5 parts in 10,000 for Eris, and about 2.9 parts in 10,000 for Make. Those are moderate values, and moderate is exactly what nobody expected. Methane inherited unchanged from the cold outer part of the disk the Sun formed from should carry a much higher deuterium fraction, because deuterium concentrates in very cold chemistry. Methane manufactured far inside a warm rocky interior, by water reacting with rock. The way it happens at hydrothermal vents on Earth's ocean floor should carry a much lower one. The measurements landed in between. One group read that as evidence for internal processing. Warm, wet chemistry inside the rocky cores of these bodies, with the products working their way up to the surface. That would mean these are not dead lumps but bodies with active interiors, doing chemistry at 4 billion miles from the Sun. A second group working with expanded data in 2025 argued the values are consistent with a primordial origin after all, if the conditions in the early disk are modelled differently. I want to be clear that this is unresolved, and I am not going to pretend otherwise. It is a live disagreement between careful people, and the honest position tonight is that we do not yet know which reading is right. But notice that both readings destroy the same assumption. Whichever way it falls, we are now measuring the isotopic chemistry of the surfaces of worlds 45 astronomical units away, and finding a signal specific enough that its interpretation matters. Nobody was doing that 5 years ago. It was not possible, and there is more from Makemake. In 2025, JWST observations found a pronounced excess of mid-infrared light coming from it, more heat than a simple inert surface should be emitting, which appears to indicate ongoing activity. The same telescope detected hydrocarbon ices and methane gas there. Gas, around a body receiving 1/2000th of Earth's sunlight. So take stock of what we have found on this part of the trip. A ring surviving where rings cannot survive. A world spinning fast enough to have been reshaped, surrounded by the debris of the impact that did it. 2 more that appear to be doing chemistry, and possibly venting gas, at temperatures where chemistry is supposed to have stopped. And I have not even mentioned Pluto properly, which is the best studied member of this class and is unambiguously alive. A plain of nitrogen ice the size of Texas with convection cells slowly turning over in it. Mountains of water ice standing 3 kilometres high. A surface in places with no impact craters at all, meaning it has been resurfaced within the last few million years, and good evidence for a liquid ocean under the shell. I keep coming back to a single word, and I think it is the word that has been quietly doing the damage. Debris. That is the word we were given for everything past Neptune. Leftovers. Scraps. The material that did not make it into anything important. It sits underneath the diagram with the band of grey rubble, and it tells you, without ever quite saying so, that there is nothing out there to think about. Rings that outlived the law that governs rings, worlds spun into new shapes, bodies still warm enough to make their own molecules, are not the properties of debris. Which brings us to a question I have been putting off. If there is that much interesting material out there, if the belt is full of objects doing things we cannot yet explain, then why is there so little of it? Because there is very little of it, and the amount that is missing is the largest unexplained fact about this entire region. Here is the number that reorganizes everything we have said so far. If you take every object in the Kuiper belt, every dwarf planet, every 100-kilometre body, every one of the estimated 100,000 large ones, and every one of the uncounted small ones, and you weigh the whole population together, the best estimates come out somewhere between 1/100th and 1/10th of the mass of the Earth. For scale, the Moon is about 1/80th of an Earth mass, so the entire Kuiper belt, everything in it, all 450,000 cubic astronomical units of it, may weigh about as much as the Moon, possibly a little more, possibly rather less. That, on its own, would just be a fact about how empty a place can be. The problem is that the objects we can see could not possibly have formed there. Run the models. To grow bodies of the sizes we observe, Pluto, Eris, Makemake, Quaoar, Haumea, and the 100,000 smaller ones, in the time available, which is something between 10 million and 100 million years, you need raw material. A lot of it. The models require a dynamically cold disk containing something like 10 to 30 Earth masses of solid material at those distances. 10 to 30 Earth masses required. Between 1/100th and 1/10th of an Earth mass present. The gap is 2 to 3 orders of magnitude. Somewhere between 99% and 99.9% of the material that was once out there is gone. And the first explanation everyone reaches for does not work. The obvious guess is grinding. Over billions of years, objects collide, break each other up, and the fragments break down further until the material is dust and the dust drifts away. But you cannot grind that much away without leaving evidence. Collisional grinding produces a very particular signature in the distribution of sizes, and the sizes we see out there do not match a population that has been pulverized by that factor. There would also be more dust than there is. Grinding contributes. Grinding is not the answer. The answer, as far as anyone can tell, is that the planets moved. This is the model usually called the Nice model, after the city in France where it was developed, and it was constructed largely to explain exactly this, the structure of the belt, rather than anything about the planets themselves. In its broad form, the giant planets did not form where we find them today. They formed closer together, embedded in an enormous disk of leftover planetesimals extending outward from them. A planet sitting in a disk of small bodies exchanges energy with them. Every close encounter throws a planetesimal one way and nudges the planet the other. Multiply that by an enormous number of encounters, and the planets migrate. Jupiter drifting slightly inward, and Saturn, Uranus and Neptune moving outward. with Neptune ploughing out through the disk for a considerable distance. The consequences for the disk were catastrophic. The overwhelming majority of that material was flung. Some was thrown inward, to be swallowed by the sun or the giant planets, or to bombard the inner solar system. Most was thrown outward, far past the belt, into the enormous faintly bound reservoir we call the Oort cloud, tens of thousands of astronomical units out. A small fraction was captured into stable resonances with the migrating Neptune, which is why the Plutinos exist and why they carry that 3-2 lock as a permanent record of the event. And a small remnant, in a region Neptune's outward sweep never quite reached, was simply left alone, which is where the cold classicals and their unbroken pairs come from. So the Kuiper belt is not a belt in any constructive sense. It is not a structure that was built. It is a residue. It is the roughly 1% that happened not to be thrown anywhere, sitting in the shape that the throwing left behind. I find that genuinely reframes the whole journey. We have been talking all night about travelling to a place, and the place turns out to be the scene of something rather than a thing in its own right. It is closer to a room that was emptied out a very long time ago than to a room that was furnished. The objects still in it are the ones that happen to be standing where the sweep did not reach. The Kuiper cliff, the resonances, the tilted hot population, the untouched cold one. All of the structure out there is not architecture. It is the pattern left by something enormous that passed through. And when you look at it that way, the small survivors become considerably more important than the large ones. The dwarf planets are interesting, but the cold classicals, in their pairs, in their circular orbits, in a band the sweep did not cross, are the only material anywhere in the solar system that was neither destroyed by planet formation nor rearranged by what came after. There is one more use the belt gets put to, and it follows directly from everything we have just said. If the orbits out there are a record of what has pushed on them, then reading the orbits carefully is a way of detecting things you cannot see. That is the entire basis of the Planet 9 hypothesis. In 2016, Konstantin Batygin and Michael Brown pointed out that a handful of the most extreme objects out beyond the belt, bodies on enormously long stretched orbits that never come near Neptune, appear to have their orbits clustered, pointing in a similar direction in space rather than being scattered at random. Their proposal was that something is herding them, an unseen body of perhaps 5 to 10 Earth masses, hundreds of astronomical units out, taking 10 or 20,000 years to orbit once. I want to be careful with how I present this, because it gets misrepresented constantly in both directions. It is a serious, published, testable hypothesis, put forward by two of the people who know this region best. It is also built entirely on a statistical pattern in a very small sample, and small samples in astronomy have a long history of producing patterns that dissolve when more data arrives. Several objects found since 2016 have orbits that do not fit the predicted clustering, and each one weakens the case a little further. The honest summary is that it might be there. The evidence has not improved as much as its proponents hoped, and the question will be settled by a sufficiently sensitive survey, either finding the thing or removing the room for it. Which brings me briefly to the version of this that has escaped into popular culture, because I get asked about it and it belongs here. The idea of a hidden massive body in the outer solar system, Nibiru, Planet X, whatever name is current, usually arrives packaged with the claim that it is inbound, that it will do something to Earth, and that space agencies are concealing it. The scientific answer is not that a distant unseen planet is impossible. We just spent 5 minutes on a published hypothesis for exactly that. The answer is about the specific claim. A body massive enough and close enough to matter to Earth on a human timescale would tug on the orbits of the outer planets and on the outbound spacecraft, and those are tracked continuously to extraordinary precision, and no such tug is there. It would also have shown up in the WISE infrared all-sky survey, which searched the entire sky at the wavelengths a cold body radiates and excluded anything Saturn's mass within 10,000 astronomical units and anything Jupiter's mass within 26,000. The same survey did the same to Nemesis, the hypothetical dim companion star once invoked to explain a supposed rhythm in Earth's mass extinctions, a rhythm which has not survived careful statistical re-examination either. There is a stranger version worth mentioning, and I like it precisely because it shows the difference between speculation and nonsense. In 2019, two physicists, Jakob Schultz and James Unwin, published a paper pointing out that if the Planet 9 gravitational signal is real, it does not necessarily have to come from a planet. A primordial black hole of about 5 Earth masses would produce the same signal, and such an object would be roughly the size of a grapefruit. It is an enormous longshot, and both authors would say so. But it is a proper hypothesis, because it specifies how you would test it. You would look for particular gravitational microlensing events, or for annihilation signatures around it. That is the dividing line, not how strange the idea is, whether it tells you how to prove it wrong. I should say honestly that this picture keeps being revised. A study in 2024 looked at what happens when you use more realistic masses for the individual planetesimals in these models, and found that the outcomes change substantially, and that the process is far more stochastic than previously assumed, meaning the belt we ended up with is one of many possible outcomes rather than an inevitable one. Run the solar system again from the same starting conditions, and the outer solar system might look quite different. Which raises a question I have no answer to, and I do not think anybody does. How much of what is out there is a consequence of physics, and how much of it is simply what happened? There is a broader version of that question too. When we look at other stars, we see debris disks, dusty rings of leftover material, and many of them appear to contain far more mass than ours does. Some of that is a selection effect. Brighter disks are easier to see, and many of the systems we can measure are much younger than ours. But it leaves open a possibility that is difficult to test and interesting to sit with, that our outer solar system may be unusually depleted, and that whatever happened here, with the giant planets rearranging themselves and clearing out 99% of the material, may not be what happens everywhere. Either way, we now know 2 things about the belt that we did not know at the start of tonight. We know it is almost entirely empty, in a way that makes arrival meaningless, and we know it is almost entirely gone, in the sense that what remains is a small fraction of what was there, which leaves one last piece of the map to deal with, the outer edge, the place where, according to every diagram, the Kuiper belt stops. That edge is real, in the sense that it is genuinely observed, and in the last few years it has started to come apart. Through the 1990s and into the 2000s, as the surveys reached fainter objects and the catalogue grew, a pattern emerged that nobody had asked for. The number of objects being found rose steadily as you looked further out, and then, at around 47 to 48 astronomical units, it fell off a cliff. Not tapered, not thinned gradually the way a disk of material ought to at its outer margin. Dropped sharply over a narrow range of distance. The feature was named the Kuiper Cliff, and it is one of the oddest facts about the outer solar system, because it is exactly the opposite of what several models had predicted. Some had suggested that beyond 50 astronomical units there should be more objects, and larger ones, since there was more room out there and nothing obvious to prevent them. The standard explanation points at Neptune, Neptune's 2-to-1 resonance, the distance at which an object orbits exactly once for every 2 Neptune orbits, sits at about 47.8 astronomical units, right where the drop happens. Resonances are powerful, they can capture objects, and they can also pump up orbits over long timescales and clear a region out. So the natural reading is that Neptune's outward migration ended near there, and the 2-to-1 resonance defines the practical outer boundary of the main population. The problem is that no model reproduces the sharpness of it properly. The observed drop is more abrupt than the resonance mechanism naturally produces, so the alternatives have accumulated. One proposal is that a body around the mass of Mars, sitting somewhere near 60 astronomical units at some point in the past, could have carved out a gap with an inner edge near 50, which would match. Another is that the original disk the Sun formed from was simply truncated, either because it was small to begin with, or because a passing star in the Sun's birth cluster stripped its outer regions early. And a third possibility, always present in astronomy and rarely as boring as it sounds, is that the cliff is partly an artifact of how we are looking, objects further out being both smaller and dimmer than anything our surveys can currently reach, so that the population appears to end exactly where our instruments do. And then, over the last few years, a plastic panel built by university students started returning numbers that did not fit. The Venetia Burney student dust counter has been on the outside of New Horizons since 2006, registering the impacts of dust grains. Dust in this region is produced mainly by collisions between belt objects too faint for us to detect directly, which makes the dust an indirect census of a population we cannot see. If the belt ends at 50 astronomical units, the dust production should fall off past that distance, and the count should drop. It has not dropped. Year after year, through the distance where the population is supposed to end, the count has stayed stubbornly, quietly high. Not dramatically so, not by a factor that would make headlines on its own, but consistently, and in the one place where consistency is the whole argument. As New Horizons has moved out through the mid-40s, the 50s, and past 60 astronomical units, the dust counter has been reading levels higher than the models predicted. A study led by Alex Doner and colleagues at the University of Colorado Boulder, published in the Astrophysical Journal Letters in January 2024, laid out the evidence and the two ways of reading it. Either the main Kuiper belt extends considerably further than 50 astronomical units, possibly out to 80, possibly beyond, or there is a second, separate belt out there, past a relative gap producing dust of its own. Independently, the long exposure observations being made with the Subaru telescope in Hawaii as part of the search for New Horizons' next target have produced hints of a population of objects at roughly 70 to 90 astronomical units, with a relative emptiness between them and the main belt. Neither result is conclusive on its own. Both point the same way. It is worth understanding why this is so hard to settle, because the difficulty is itself part of tonight's story. Brightness falls off with distance twice over. The sunlight reaching an object falls with the square of its distance from the sun, and then the reflected light reaching us falls again with the square of its distance from us. Combine those and you get something close to a fourth power law. Move an object from 40 astronomical units to 80, and it becomes roughly 16 times fainter, before you account for the fact that anything that far out is likely to be smaller as well. Objects at 80 astronomical units are not slightly harder to detect than objects at 40. They are in a different regime, and most of them are simply beneath the noise, which is why so much of the work out here is being done by methods that do not require seeing the object at all. Occultations are one. You do not need to detect the body, only to notice a star it passes in front of. There are projects now running fast photometry arrays specifically to catch these events by chance, monitoring thousands of stars at high frame rates, waiting for millisecond blinks, in the hope of building a statistical census of objects far too faint to image. Dust counting is another. Both are ways of measuring a population by its effects rather than its appearance, which is what you do when the appearance is not available. The other thing that keeps this unsettled is that the size distribution itself is strange. Detailed surveys of the cold classical population have found that the number of objects does not continue smoothly upward as you go to smaller sizes the way a simple grinding process would predict, and that above a few hundred kilometres the population essentially stops. There is a shape to the population that models have to reproduce, and reproducing it and the cliff and the mass deficit all at once with the same history is genuinely difficult. Real help is arriving, and it is arriving now. The Vera Rubin Observatory in Chile has begun its 10-year survey of the southern sky, and it is expected to increase the known catalogue of objects beyond Neptune by roughly a factor of 10. A dedicated faint object survey along New Horizons' own trajectory, led by J.J. Cavalaz, is intended to determine orbits for something like 700 Kuiper belt objects. That is the scale of instrument it takes to answer these questions, and it is only just switching on. So the outer wall of the solar system's populated zone, the edge on the diagram, the thing that made the belt look like a belt, may turn out to be a limit of our instruments rather than a fact about the solar system, and if it is, then the sharpness of the cliff is not a mystery about how the disk was sculpted. It is a mystery about why we could see this far and no further, which is a much less interesting question, and a much more embarrassing one. I want to point out what the instrument was that did this, because it is a small thing, and I think it matters. It is not a flagship telescope. It is not a billion-dollar observatory. It is a sheet of plastic film about the size of a large book, wired to register electrical pulses built by students, flown as a secondary payload because somebody thought it would be a good educational project, and left switched on for 20 years while the expensive instrument slept. And it may end up rewriting the outer boundary of the solar system as it appears in every textbook. There is a nice symmetry in it too. The panel is named for a girl who was 11 years old in 1930, eating breakfast in Oxford, when her grandfather read out the newspaper story about a new object found beyond Neptune that did not yet have a name. She suggested Pluto. Nearly 80 years later, a detector carrying her name was bolted to a spacecraft, sent to that same object, and is now quietly redrawing the far side of it. That is also, incidentally, the answer to a question people ask about missions like this. Why keep an old spacecraft running when its main job is done? because the main job was never the only one, because a machine that is simply present in a place nothing else has ever been, taking the most basic possible measurement continuously for 2 decades, will eventually notice something that nobody thought to look for. And this brings the video to the place it has been heading all along, because there is a hard problem sitting underneath all of this good news. If the belt extends to 80 astronomical units, or if there is a second belt beyond a gap, then the region we have been calling the Kuiper belt is even larger, even emptier, and even more thinly populated than the arithmetic we did earlier suggested. The objects are further apart, the chance of any given trajectory passing near one is lower, and the target list, the set of specific bodies you could actually steer a spacecraft at, does not grow, because the things producing that dust are by definition too small and too faint for us to have catalogued. We have found the region is bigger. We have not found anything new to visit. Those 2 sentences do not sound like they belong together, and I think the fact that they do is the single most underappreciated thing about exploring the outer solar system. Knowing that a population exists and being able to reach one member of it are almost entirely unrelated problems. Dust tells you there are objects. It does not tell you where any particular one is, and a trajectory needs a particular one. And there is exactly one machine out there, right now, with the ability to visit anything at all, and it has spent a decade looking for something to look at and has not found it. Let us stop moving outward for a few minutes and put everything we have collected in one place, because the pieces have been arriving one at a time, and the shape they make only appears when you set them side by side. We started with a picture, a dense band of rubble past Neptune, a wall to be crossed, a frontier. The first thing to go was the danger. The volume out there is so large, and the objects so few, that the average spacing between 100-kilometre bodies is something like 150 million kilometres. The dust density is 1 grain in every 50 million cubic metres. Nothing has ever been hit, out here or in the asteroid belt, by any spacecraft we have sent, and nothing was ever likely to be. The crossing is not merely survivable, it is uneventful in a way that is difficult to convey. The second thing to go was the arrival, because if the objects are that far apart, then being inside the belt is not an experience. You could stop at a randomly chosen point in the middle of the most discussed structure in the outer solar system and see, with your own eyes, exactly nothing. A brilliant point of sunlight behind you, a black sky full of unchanged constellations, and no horizon, no landmark, no motion, and no sense whatsoever of having got anywhere. The instruments would say you had arrived. Nothing else would. You cannot arrive at a probability. I said that lightly in the fourth part, when we crossed a line that has no physical existence, and I want to give it its full weight now, because it is the fact that everything else in this video hangs from. The Kuiper belt is a statistical description of where certain objects tend to be. It has no surface, no boundary, no centre, no landmark, and no address. It is not the kind of thing that can be visited, and that means the entire framing of the journey, go to the Kuiper belt, arrive at the Kuiper belt, is a category error, in the same way that sailing to the middle of the Atlantic is not the same as sailing to an island, which leaves only one kind of real destination out there, a specific object, a named body with a catalogued orbit whose position you know precisely enough to intercept. And now stack up everything we know about what that requires. You cannot slow down, so it is a flyby, and the useful window is minutes long. You cannot steer at the last moment, because the one-way light time is hours and nothing can be corrected. You must therefore have aimed correctly years in advance. Aiming requires the object's position to be known to within a few kilometres, which for a faint body 4 billion miles away requires either the Hubble Space Telescope or a network of occultation observers standing in the right narrow shadow track on Earth on the right night. And all of that has to be arranged for an object that lies within the small cone of space your remaining fuel can still reach. That is the actual difficulty of exploring the Kuiper belt, not the distance, not the cold, not the emptiness in the sense of danger. The problem is that after you have paid the enormous price of the distance, you arrive in an ocean of nothing, and unless you already knew which specific grain of the dark to point at before you left, you have bought yourself nothing at all. And we know exactly how hard that problem is, because we are watching somebody fail at it right now. New Horizons has been looking for a third target since 2019. The Subaru telescope has run something like 30 half-nights of dedicated searching in support of that effort, and has turned up more than 240 objects out beyond Neptune. 240. It is a genuinely impressive haul, and it has produced real science about the structure of the region. Not one of them is reachable. Every single one requires more fuel than the spacecraft has left, or sits outside the cone it can still turn into. The search continues. The team has brought machine learning tools to bear on picking faint-moving specks out of the crowded star fields toward the galactic centre, and the Rubin Observatory survey is beginning. But as of tonight, the only machine humanity has in the Kuiper belt has nothing to visit, and time is not on its side. The obvious response to all of this is to say, fine, then stop building spacecraft that cannot stop. Build one that can go into orbit around a Kuiper belt object and stay there. And that is exactly right, and it is exactly what the people who work on this would like to do, and it is worth understanding why it has not happened. To orbit something out there rather than flying past it, you have to shed most of your arrival speed. New Horizons arrives at around 14 kilometres per second. Orbital speed around a body a few hundred kilometres across is a few meters per second. So you need to lose essentially all of it, at the far end, having carried the means to do so for a decade. With chemical propulsion that is not expensive, it is impossible. The rocket equation turns it into a fuel mass no launch vehicle could lift. The way out is to stop treating propulsion as something that happens in minutes. Electric propulsion, ion engines or something nuclear electric, produces a very gentle thrust continuously, for years. The push at any instant is roughly the weight of a sheet of paper on your hand. But run it for a decade and it can change a spacecraft's speed by more than any chemical stage, because it uses its propellant far more efficiently. Mission concepts for a Kuiper belt orbiter have been studied more than once. One of them, a design called Persephone, sketched a mission of roughly 50 years flight time and several $1 billion, and none has ever been funded. And underneath that sits a constraint most people have never heard of, which quietly limits everything humanity does past Jupiter. There is no sunlight out there worth collecting, so any mission needs a nuclear power source, and that means plutonium-238, and plutonium-238 is not something you can buy. It has to be manufactured, deliberately, in reactors, a few kilograms at a time. Production in the United States stopped for decades, and has only recently restarted at a modest rate. The number of outer solar system missions that can exist at any given time is set, in a very literal sense, by how many kilograms of a specific isotope exist. So the honest summary of where we are is this. We can reach the Kuiper belt, we have done it. What we cannot currently do, for reasons of propulsion, power supply, funding, and, most of all, target availability, is stay. So here is where we have arrived, one part before the end. We came out here expecting a frontier and found a probability distribution. We came expecting danger and found the best vacuum in the solar system. We came expecting darkness and found permanent twilight with a razor-edge shadow and a sky full of stars at noon. We came expecting debris and found rings that outlived the law of rings, a world spun into a new shape, bodies still doing their own chemistry, and pairs of objects that have been circling each other, untouched, since before the Earth existed. We came expecting a belt and found the 1% that survived a sweep, and every one of those corrections has made the region more interesting and less reachable at the same time. It is worth saying out loud how thin the evidence for all of this is, because it is easy to lose track when the facts are delivered confidently. Everything I have described about what these worlds are like at close range comes from two flybys. Pluto, in July 2015, Arakoth, on the 1st of January 2019. Between them, less than a day of genuinely useful close observation, gathered by one spacecraft in 13 years. Everything else, Quao's ring, Haumea's shape and family, the isotopes on Eris and Makemake, the binary fraction of the cold classicals, the mass of the whole belt, comes from starlight, collected from 150 million kilometres inside Earth's orbit, and from stars blinking out for fractions of a second. That is not a criticism. It is a remarkable achievement, and it is how almost all of astronomy works. But it means that our entire close-range knowledge of a region containing more than 100,000 large bodies rests on a single day's looking, and everything I have told you tonight could be revised substantially by the third encounter, whenever it happens, if it happens. Which finally brings us back to the question I asked at the beginning of tonight, and which I have been deliberately not answering for the last 2 hours. If you went, if you crossed the 4 billion miles and stopped and looked around, what would you really find? I can tell you now. You would find the first draft. That is the answer, and I want to unpack it properly, because it is not a metaphor, and it is the only thing out there that justifies the price of the trip. Every world in this solar system that we can easily reach has destroyed the record of its own construction. That is not an accident. It is a consequence of being large. A body big enough to become a planet is big enough to heat up, from the energy of its own assembly, from the decay of radioactive elements in its interior, and once it is hot enough, it melts. Once it melts, the heavy material sinks and the light material rises, and everything is sorted by density, and whatever original structure the object had is gone forever. Then the surface gets cratered and resurfaced and weathered, and in our case covered in oceans and continents and rebuilt from underneath many times over. Earth is the extreme case. There is almost no rock on this planet older than 4 billion years, and there is none at all from the first few 100 million. The story of how the Earth was assembled is not written down on the Earth. It was erased by the assembling. The Moon keeps more and Mars keeps more, but both were shocked and cratered and heated. Meteorites keep more still, but they arrive as fragments, torn out of context, having survived being blasted off something and then falling through an atmosphere. Comets come from out here, but they arrive cooked, having been heated repeatedly on their passes around the Sun. And then there is a band of space between roughly 42 and 47 astronomical units, in permanent twilight at 30 to 40 Kelvin, containing objects on almost perfectly circular orbits, some fraction of which are in pairs so loosely bound that a single close encounter in 4.5 billion years would have separated them. They were never heated enough to melt. They were never hit hard enough to shatter. They were never scattered near enough to a planet to be pulled apart. Nothing happened to them at all. That is what you would find, not debris, not leftovers. The original material of the solar system, in the configuration it assumed on the day it was made, sitting exactly where it was made, at the temperature it has always been, with the chemistry it started with still on its surface. The two lobes of Arakoth drifted together at walking pace before there was an Earth, and they are still touching. That is the thing. That is what the 4 billion miles buys you. Not a landscape, not a view, not a moment of arrival. A set of objects that constitute the only surviving copy of the instructions, in a solar system where every other copy was destroyed by the process of following them. There is a second thing you might find, and I want to flag it clearly as speculation, because it is speculation built on one solid measurement rather than on nothing. Pluto, the one large body out there we have looked at closely, shows good evidence for a layer of liquid water beneath its ice shell, kept liquid by leftover heat from its formation, and by the decay of radioactive elements in its rocky core, with ammonia and salts acting as antifreeze the way salt keeps a road wet below freezing. That is one object, measured once, in passing. But if the same physics applies to bodies of similar size and composition, then it applies to a great many things out there. There are estimated to be more than 100,000 objects above 100 kilometres in the belt, and perhaps 10 or more in Pluto's size class, which raises a possibility that is difficult to test and, I think, quite hard to shake off once you have heard it, that the outer solar system may hold more liquid water, by volume, than the inner solar system does. Not on the surface, not anywhere warm. Kilometres down, inside bodies we classified as debris, permanently outside every habitable zone anyone has ever drawn on a diagram. I am not telling you there is anything living in it. Nobody knows, and the honest answer is that nobody is close to knowing. What I am telling you is that when we drew the region we would look for life in, we drew a narrow band around the Sun, and we drew it before we knew what was out here. And now the second half of the answer, which is the part that has been running underneath this whole video, and which is the reason the word in the title is terrifying. We have one machine out there. New Horizons is somewhere past 60 astronomical units now, about 9.5 billion kilometres from Earth, moving outward at roughly 14 kilometres per second, and receding by something like 480 million kilometres every year. Its signals take around 9 hours to reach us. In July of this year it woke from the longest hibernation of its mission, in good health, and resumed work. Its mission is currently funded through 2029, and the plutonium is running down. It has been running down since the day it was made. By around 2038, the generator's output is expected to fall below 100 watts, and from there, the instruments have to be retired one at a time as the budget shrinks. The mission team believe there is enough propellant and power to keep something running into the 2040s, out past 100 astronomical units, but the direction of travel is fixed, and it is downward, and it is not a failure or a malfunction. It is arithmetic. It was arithmetic on the launch pad in 2006. So let me put you in the last moment of this journey. It is some evening in the 2040s. The spacecraft is intact. Nothing has broken. It is still pointed correctly, still moving outward at 14 kilometres a second, still carrying 30 grams of the ashes of the man who found Pluto. But the heat coming off the plutonium has fallen past the point where the instruments can be run, and one by one they have been switched off to keep the transmitter alive, and then the transmitter goes too. 9 hours later, on Earth, in a control room where the seats have been reassigned and most of the original team retired long ago, a signal that will never come does not arrive. Nothing dramatic happens. There is no explosion, no loss of control, no crisis. The machine simply stops being able to say anything and continues outward, and will continue outward for millions of years. And on that evening, unless something changes, the human presence in the Kuiper belt returns to zero. There is no funded successor, no orbiter, no second flyby mission. No replacement is currently built, budgeted, and scheduled. The concepts exist on paper and have existed for years. The Rubin Observatory survey that might, if we are fortunate, find one last object inside the small cone of space New Horizons can still reach, is only beginning now, and the spacecraft is running out of both fuel and time to use it. I said earlier that nothing out there is going dark, and I meant it literally. The sun will keep delivering its 60 lux to those red surfaces long after every one of us is gone. Arakoth will keep its two lobes touching for billions of years. The binaries will keep circling each other at a few meters per second, undisturbed, exactly as they have since before the Earth had a crust. Not one of those things needs us in any way at all. Twilight, not darkness. What goes dark is not the Kuiper belt. It is us. It is the looking. For a period of about 40 years, from a spacecraft leaving Florida in 2006 to a transmitter falling silent sometime in the 2040s, our species had one machine inside the only archive of its own origins that survived, and used it to look closely at two objects for a total of less than a day, and then stopped. The archive is not going anywhere. It will still be there, unchanged, at 44 astronomical units, in the permanent twilight, cold enough that nothing can react and therefore nothing can be erased. It is simply that nobody will be reading it. So that is the terrifying journey to the Kuiper belt, and that is what you would really find. Not danger. There is none. Not a frontier. There is no line to cross. Not even, in any way your senses could confirm, a place. You would find the emptiest volume anyone has ever travelled to, and scattered thinly through it, at intervals of 150 million kilometres, the only unaltered pieces of the beginning of everything, still touching, still red, still exactly where they were left, and a small cooling machine, moving away from them at 14 kilometres a second, with the lights going out one at a time. Sleep well,